So in this example, we're going to look at a more complicated problem. This is typically called a chase problem, where we have some kind of chase going on, where something catches something else. So in this one, we have a car, and it's moving, it's speeding. It's going 30 meters per second down the street when it passes a police car. The police car is parked on the side of the road, and the police car begins to move 1 second after the car passes, and then accelerates at 4 meters per second squared. So we'll model this out, and then we'll answer all the questions that we could. So just thinking about this, it's like, you know, the cop car is sitting on the side of the road with he's at rest, the initial velocity, and then this other car comes flying by. So he comes passing by, and after 1 second has passed, you know, the car's over here somewhere, but he's moving. And so we're going to assume he's speeding at 30 meters per second. We assume that the car is constant velocity, that he just keeps moving at 30 meters per second. And then after 1 second, the cop car takes off, but the cop car is accelerating. So this one is constant acceleration. So we're going to have two different models here. I mean, they're both constant acceleration, but this is acceleration 0 for this one. Okay, so the first thing I'm going to do is just kind of draw out this, but you know, thinking about where things are and the time and all of that. So we have, well, let's just begin at the beginning. So when the cop car starts moving, and that's kind of what we want to be concerned with. And so I'm going to we'll put the car up here and the police down here. So the police, he's sitting right here, and after 1 second, this other car is way over here. So he's got a head start. Okay, so now we can identify where some things are. We would say, you know, basically this is going to be time is 0. For both of these, you know, this is time is 0. So we'll say this is where he is at time equals 0. This is where he is at time equals 0. But they're obviously not at the same position. So now we have to figure out what's the position. This one we could call 0. So we could say this initial position is 0. We also know the initial velocity is 0. Okay, so those are the quantities we know for this one. Over here we need, we know that the velocity, I'm kind of out of room, but we know the velocity is 30 meters per second. And then we also know that he's moving at 30 meters per second, because that's how fast it's constant. When he passed right here, he was moving at 30 meters per second, so how far did he go in 1 second? Well, then he went 30 meters, because he's doing that every second. So this x naught is 30 meters. So you can see they have different initial positions, but they're going to have the same initial time and then different initial velocities. All right, and then what happens is this guy keeps moving at the same velocity, constant velocity, and meanwhile the police officer starts speeding up. And eventually he's going to catch him. You know, I don't know where, somewhere over here, they're going to catch. But if I think about it, when he catches him, what has to be the same? Well, they're going to have the same final position, because he's caught him. Okay, let's sketch the graphs, and maybe we can make some sense of it. So let's do the position time graph. Oops, I was thinking of the car and I wrote a C. So the position time. Okay, so the car begins at 30. I'm sorry, at 30 meters down here. So somewhere right here, you know, like 30. That's how fast that's where it is to begin. And it's going at a constant speed, so we know that this is a line. So it's going to go up like this. So that's the car. I'll just use C for car. Constant velocity is always a line. And the police officer, he's speeding up. Now he starts at a position of 0, so he's going to start at the origin. But he's speeding up, so we're going to end up with a quadratic. So we end up with something like this. And it's this point right there, that's where he catches them, because this is a position graph. So they have the same position right here. So the time is going to be the same, and the position is the same, xf. Now we don't know either of those quantities. All we know is the velocity and how far he was and the acceleration. But that's our position time graph. So we can see that the cop catches up. Oh, that's a police officer. Okay, so now let's look at the velocity graph. So velocity versus time. So the car is moving at a constant velocity, so it's like this. That would be the car. And then the police officer, he's speeding up, so his velocity is increasing. Like that. And you might look at this graph and think, oh yeah, there's where he catches him. No, that's where they're the same speed. He's actually going to have to go faster than the car. It's going to be over here somewhere. So we'll have some time here, which corresponds to some velocity, final velocity of the police car. And then finally, we can do the acceleration. I'll come back up for the rest of the model. Acceleration over time. So the car is not accelerating; it's moving at a constant velocity. So that graph is down here. That would be the car. But the police car is accelerating. He has some positive acceleration. And it's, I think it was 4. Yeah, 4. So we can go to put 4 on there. And that's meters per second squared. Okay, cool. So there's our model. We can now start diving into some equations. Now, I know that what I really want to find is what time does the police car catch up, and how long does it take to catch up, and where are they? So these are going to be the primary questions that we could answer. Once we have that, we could figure out, well, how fast is the police car going when he catches them? So let's start with our position function, and I'll just separate this. I'll do the car over here, and we'll do the police over here, and see what happens. We'll just try, and maybe we go down a dead end. So the position is given by the initial position plus the velocity times time plus 1/2 the acceleration times time. Notice I write it all out, and then we go back and figure out if we can cancel anything out. So the final position, I don't know what that is. But I know the initial position, that's 30. And I know the velocity. The initial velocity is the same throughout, it's 30. T. And I know that there's no acceleration, because it's constant velocity. So we just get this. So I have 2 variables that I don't know. So we're going to have to figure out a different equation. So let's go to the police car. So the police car, again, I'll start with this. X is x naught plus v naught t plus 1/2 at squared. So we have the position of the police car. And what we can do, since I have 2 x's, I'm going to put a little p there, and I'll put a c here. So that's the position of the car and the position of the police, is the initial position. But the initial position I said was 0. So that's gone. The initial velocity is 0 because he started from rest. So we just have this, 1/2 of the acceleration, which was 4, times t squared. And then if we just simplify that, we get 2t squared. And the key to this is going to be that when he catches them, they have the same position. They have the same position. So what I can say is that the position of the car has to be equal to the position of the police, and that's when they catch them. And now we'll just substitute. So we'll put this one in there and this one in there. So we get 30 plus 30t equals 2t squared. So now I have an equation which only has one variable, but it's quadratic. So we're going to have to do it in quadratic. So I'll move everything over, set it equal to 0. So I get 2t squared minus 30t minus 30 equals 0. And I can divide off this 2. So t squared minus 15 to t, I'm just dividing everything by 2, minus 15 equals 0. Okay, at this point, so now, because these are both 15, I'm going to have to use the quadratic formula. So you plug it in the quadratic formula, and you get the time is equal to positive or negative 15.94. Or no, I'm sorry, that's not right. It's not positive or negative. You'll get a negative, or you get a negative value and a positive value. So the negative value, if I think about it, if I go back here, if I continue this and go backwards, it's going to do this. And then if I take this one backwards, it goes like this. So the negative value is this point over here. That's not what I want. I want this one, the positive value. And the positive value out of that is going to be 15.94 seconds. So that's this time here. So we know that he catches them after almost 16 seconds, 15.94 seconds. But that doesn't answer where they are. So to get where they are, I just take this and plug it in back in here, because they have the same position. So either one of these, I can plug it in. So I'll go ahead and plug it in this one. So x of the car equals 30 plus 30 times 15.94. So we get x of the car is, I need to calculate it real quick, 30 plus, I get 508.2 meters. So about half a kilometer. And just for sake of checking it, I can plug it in this side too. So the position of the police car is 2 times that squared. So I get xp equals 2 times 15.94 squared, and I get 508.2. So you can see they're at the same position. So the police car has caught them. So now we have this value, the 508.2. The only value that we don't know is how fast the police car is going. So to do that, we would use the velocity, which is the initial velocity, plus the acceleration times time. He started at rest, so it's just going to be the acceleration, which is 4 times the time, 15.94. So we get 4 times 15.94, 63.76 meters per second. So he's going crazy fast. Yeah, that's really fast. So really, there's probably no way that this would have happened. He couldn't catch him. That's about, it's well over 150 miles an hour or something like that. Man, that's really fast. I made up these numbers, so let me see. Just curious. I'm going to do 63 meters per second, 2 miles per hour. It's 140 miles an hour. So when he catches them, he's going to have a hard time pulling them over because he's going to fly by him. But that's what this kind of shows. He's going to fly. Whoa, you see the velocity is really high? Because this guy was at 37. This guy's at 63. So he's going nearly double. Anyway, so this is a more complicated problem, but what I wanted to show you is that we take the same basic approach. We just kind of draw it out, label what we know, maybe sketch some graphs so we can think about what the problem is before we get into the math. And eventually what you'll be able to do is just kind of draw these initial and final kind of things, and you should start to kind of see like how you could dive straight into the math. But you don't want to do that for quite a while, okay? So always draw pictures, use your graphs to think about the problem, and everything will be okay.